Aloha! Welcome to the presentation Testing the Water, Basic Water Quality Testing for Aquaponic Systems. I'm Ruth Ellen Klinger-Bowen. I'm a researcher at the University of Hawaii that's been working with aquaponics for 10 years, primarily in water quality, fish health, and disease issues. This presentation is part of the University of Hawaii at Manoa College of Tropical Agriculture and Human Resources Virtual Livestock Industry Field Day Series. What water chemistry parameters should you test for? First, you need to ask these questions. What water chemistry measurements do I need to know for good plant health? What measurements do I need for proper fish health? And lastly, how much will it cost to do these tests and still be accurate measurements? Fortunately, most water chemistry parameters that you need to measure are important for the plants, the fish, and the drivers of the system, the bacteria. They are temperature, dissolved oxygen, pH, ammonia, nitrites, nitrates, conductivity, and/or total dissolved solids. The nitrates, conductivity, and total dissolved solids are most important for good plant growth. Let's look at each of these and why we need to test these in our aquaponic system. Water temperature is very important in aquaponics as it affects the whole ecosystem, the plants, the fish, and the bacteria. High temperatures will increase ammonia toxicity in fish, as well as decrease the amount of oxygen in the water. Too low temperature decreases a fish's immune system and can potentially make them more prone to disease. Know your plant's temperature tolerances and try to grow like temperature plants together. An important note is it isn't necessarily the temperature itself that can be the problem, but the sudden shift from hot to cold or cold to hot that will cause harm. Even in Hawaii, we can have sudden temperature shifts, particularly in the higher elevations. Water temperature is easily taken with an aquarium thermometer. Also, low-cost electronic pens and meters that measure other water chemistries often have the added capability of measuring temperature. Dissolved oxygen, or DO, is the amount of oxygen dissolved in water. Fish and plant roots need adequate oxygen. Also, the bacteria that cycles the nitrification process need adequate oxygen. It is measured as parts per million, ppm, or percent saturation. Make sure the DO is at least 6 parts per million or 80% saturation. There are some chemical test kits that do measure DO, but the simplest method is a low-cost battery-operated DO meter. Remember, the higher the water temperature will decrease the dissolved oxygen levels. Also, biomass, which is the weight of fish and plants to water volume, will also affect DO levels. pH stands for the power of hydrogen. It is the negative logarithm of the concentration of hydrogen ions, symbolized by H+, in the water. It is a negative scale from 1 to 14, with 1 having the highest amount of hydrogen ions, called acidic, and 14 having the lowest hydrogen ion concentration, called basic. pH 7 is neutral. Because it is a negative scale, a pH of 7 has less hydrogen ions than a pH of 6. A logarithmic scale means it's a 10-fold scale, so a pH 7 has 10 times less hydrogen ions than a pH 6, and 100 times less hydrogen ions than a pH of 5. Why is pH so important to know? If pH is too low or too high, fish, plants, and the nitrifying bacteria will adversely be affected. Along with too high temperature, too high pH increases ammonia toxicity to fish. Fortunately, too high pH in aquaponics is rarely a problem, as the natural nitrification process over time lowers the pH, often so low that a buffer, such as crushed oyster or coral, needs to be added. We'll discuss this further in later slides. This chart shows what crops do well at what pH ranges. It also shows the best pH range for proper fish and bacterial health. Note, for all three entities to be happy, the pH range is fairly narrow, so try to maintain a pH of 6.5 to 7. pH is measured with many easy methods, from chemical test kits to low-cost battery-operated meters. I do suggest, if you use an aquarium kit, to also purchase a hydroponic pH kit. Most aquarium kits only measure down to a pH of 6. You could have a much lower pH than 6 and not know it until it was too late. Hydroponic kits have much lower pH ranges. This graph shows what of the many macro and micronutrients that plants need are available at what pH. Again, maintaining a pH of 6.5 to 7 will be sufficient for these nutrients to be available for your plants. I've been mentioning the nitrification process and the nitrifying bacteria in past slides. What exactly is this process? It's also called the nitrogen cycle. There are three main components of the nitrogen cycle which need to be measured for the overall health of your aquaponic system. They are ammonia, nitrites, and nitrates. When we feed the fish, the protein from the fish feed is metabolized by the fish and excreted the waste product as ammonia. The nitrifying bacteria, which naturally occurs in the environment, converts ammonia to nitrite and then from nitrite to nitrate. Plants are known to utilize all three nitrogen products, but they prefer nitrates. The test methods available measure the total ammonia nitrogen, often abbreviated as TAN or TAN. TAN consists of two forms, an ionized form, NH4, which is not toxic to fish, and an unionized form, NH3, which is toxic to fish. How much is in one form or another is dependent on temperature and pH. The higher the temperature and/or pH is, the more toxic ammonia will be present. Ammonia only affects the fish by decreasing the fish's tissue structure and function. Even a low amount of toxic ammonia can cause fish to spin, become disoriented, and even die. This is rare in aquaponics as we try to keep the pH at 6.5 to 7, where toxic ammonia is typically 0. Nitrites also only affect fish's health. You should always make sure nitrites are 0, as it prevents oxygen from entering the fish's bloodstream. If nitrites are present, the gills will have a brownish coloration rather than the normal reddish color, which is why they call it brown blood disease. Nitrates are rarely toxic to fish. Most species can tolerate levels higher than 400 parts per million. Typically, nitrate levels are maintained from 50 to 150 parts per million for good plant production. Ammonia, nitrites, and nitrates are easily measured with chemical test kits, either with an aquarium water test kit or a fish farming or aquaculture water test kit. How quickly the bacteria can convert ammonia to nitrite and then to nitrates is dependent on a number of factors, including oxygen, temperature, pH, and buffering capacity of the water. What is buffering capacity? It is often called and measured as total alkalinity. It is the water's ability to maintain a fairly constant pH. It's expressed as parts per million calcium carbonate, milliequivalents per liter, DKH, or just KH. Carbonates and bicarbonates are the primary sources for alkalinity measurements. In freshwater, keep total alkalinity between 50 and 200 parts per million. This can be accomplished by keeping crushed coral or oyster shells in the fish tank. The rule of thumb is 1 to 2 pounds of calcium carbonate source for every 100 gallons of water. Total alkalinity is measured typically with a chemical water test kit, which you can get from aquarium stores or an aquaculture supply shop. Conductivity measurement is important for plant production as it is a marker for the macro and micronutrients. In other words, the ion content. The higher the ion content, the higher conductivity will be measured. You will need to buy a battery-operated meter to measure conductivity. It's measured as microsiemens per centimeter or millisiemens per centimeter. Instead of measuring conductivity, most aquaponic users find measuring total dissolved solids, or TDS, easier to use. Also, a TDS meter is generally less expensive than conductivity meters. However, there are some meters that measure both. Just know that 1 part per million TDS is equal to 2 microsiemens per centimeter of conductivity. What exact method you use to measure the specific water chemistry parameters can be daunting, as there are many methods out there. Test strips seen at the top left, to aquarium kits on the top right, to aquaculture kits on the bottom left, to meters on the bottom right. There are pros and cons for each of these methods. Test strips are easy to use, but they're not very accurate, whereas meters are very accurate, but you need to have periodic calibration. How do you decide what is right for you? It really depends on how many tanks or systems you need to measure. Chemical test kits are great if you're measuring just a tank or two, but if you have multiple tanks or systems, you may want to invest in more expensive meters. It also depends how often you test, how long will the test method last while still being effective and efficient, and how much you want to spend without compromising accuracy. For a backyard aquaponic system, I recommend having an aquarium test kit that can measure pH, TAN, nitrites, and nitrates, a hydroponic pH water test kit, or even better, a pH pen meter, a total alkalinity water test kit, a TDS meter, and a DO meter, which also will record temperature. Whatever method or methods you decide to use, make sure you take records of when and what was measured and each of the parameters values. This is an example of a record log showing the date, the method used, tank number if needed, and the value for each of the important water chemistry measurements. So, how often should you take measurements? It is recommended that temperature, DO, pH, and total dissolved solids be taken daily, as these can change day to day. If you're just starting out with a new system, check the TAN, nitrites, and nitrates every couple to 3 days. Once the system is cycled, you can take the nitrogen components 1 time a week. If you're a teacher, taking water chemistry is a fun and useful tool for your students to learn chemistry and about ecosystem health. Just remember, record those measurements. Here are a few publications that may be of interest to you. The first is a good publication on small-scale aquaponic systems. The latter compares different water chemistry methods for an aquaponic system, listing the pros and cons of each. Mahalo for listening, and have fun taking water chemistry in your aquaponic system.